Brief. Hello, everyone. I want to welcome you to the first session of WOLA 2020. I also want to mention again that we are being recorded, so you should be aware of that. This session is going to feature an invited talk by Madhu Sudan and 4 short talks by Jonathan Tidor, Marcel Del Agnol, Yanjun Han, and Ziteng Sun. So let me give a quick introduction of Madhu. I want to keep this short because every second I'm speaking, we're not getting Madhu speaking. Madhu is the Gordon McKay Professor of Computer Science at Harvard. We all know he's a towering figure in our community. He's done fundamental work in lots of areas: property testing, PCPs, complexity theory, coding theory, communication, the list goes on. He has a dazzling list of awards and honors: the Nevin Lina Prize, the Infosys Prize, National Academy of Sciences, American Academy of Arts and Sciences, et cetera, et cetera. He's also a really nice guy, a fantastic teacher and lecturer, so we're really in for a treat. I should be quiet now and let us get as much of Madhu as possible. He's going to be telling us about communication amid uncertainty. So welcome, Madhu.
Thanks, Rocco. Thanks to all of you for being here. Rocco, you're doing very well. In fact, I wouldn't have minded you going on for another 40 minutes, and then I think I would have been pretty happy. Let me try sharing my screen here as I do that. Okay. All right, so, I know many of you are by default muted, but if you try to ask questions on chat, if I don't catch it, hopefully Rocco or somebody will catch it and relay it up. So this is work that I've been doing for many, many years now, and trying to deal with communication as a, in a somewhat different setting than what we've been usually studying. So here's the obligatory sales pitch. So most of communication theory, if you think about Shannon, Hamming, et cetera, have always been built around this notion that the sender and the receiver are perfectly synchronized objects. And in contrast, most of human communication doesn't really assume such synchronization. So before we got into this meeting today, we didn't exactly agree on the set of definitions that are legitimate and the other things that have to be recalled or redefined. We just enter a conversation without perfect synchronization. At the same time, I think it's very important to notice that in both settings, context is treated very differently. So in large amounts of human communication, when you have not synchronized, context, how do you actually try to get to agree on things? In contrast, when you're designing communication, large amount of context, if you want it, that's fine. So if you want to say that this code is known to the sender, error correcting code is known to the sender and receiver, fine. This protocol of communication is well known in communication complexity, fine. You have the following priors on how the inputs come, fine. All of this can be baked into the problem, whereas in human communication, these are issues that you have to deal with. And what this talk is really an attempt to, I try to understand context. And this context is something that I believe is relevant qualitatively, because if you don't take it into account, you can have, receiver of information can take the wrong action based on the signals that they're receiving. And it's also quantitatively important because suddenly when you start putting the context in as part of the inputs that players have, inputs become excessively long. So if you want to say the context for today's talk is some English and some math, that's a huge amount of information that we are counting on. And it will vastly scale your notion of n that we worry about. If normally we would think square root of n communication is good, now it's no longer feasible. That's square root of the length of the English dictionary. So these things led us to ask the question, we should build a theory, but then question sort of, once you say, well, we want a theory, start asking what are the problems? Can you make them concrete in some mathematical sense? And what are the starting points for a theory of communication? A natural starting point would have been Shannon's theory, but as we will see shortly, it's really Yau's theory of communication complexity that seems to be the right framework in which we want to study this. In a nutshell, Yau's theory allows us to put in, give players huge inputs, the context, etc., and still allow for very short communication between sender and receiver in order to achieve a certain task. So this is the notion that is very appealing to us, and that's why we will be following this framework. So just to make sure we are all on the same page, this is communication complexity, something that we understand very well. Alice and Bob have some inputs, X and Y, and then they have some additional function that they want to compute. And let's say for simplicity in this setting, Bob wants to compute this function. This will also allow me to talk about one-way communication, where Alice sends Bob some information, but it's only Bob who is able to compute the value of the function. And the communication complexity is the minimum number of bits exchanged by the best protocol that you can have. And we will be considering a setting with shared randomness. So Alice and Bob will share some amount of randomness. Both of them know this, and it's not counted as the budget on the number of bits that are exchanged by the protocol. You have this common randomness, and you can use it as freely as you want. Now, communication complexity is, of course, widely studied, and we have books and books and books written on it. They start off with chapter 1. Here's the model. Chapter 2. Here are some lower bounds. So what's different about this talk is that we're going to be talking about communication complexity as really a positive model. Of course, we will also be proving some lower bounds, or at least we'll mention some lower bounds. There won't be any proofs in this talk. But really, where was the second chapter of the book, which was here are protocols, right? And I think that's something that's been we've often overlooked in communication complexity. There are actually very interesting tasks that can be solved with very little communication, even though the input lengths of the players are pretty large. Okay. So I want to tell you a little bit about those. So this is going to be a bit of an aside, but I think this is sort of one of the more fun parts of the talk. So it gives you something to think about. What are some communication complexity problems that are actually easy? And to make this sort of the extremal thing, players will have inputs of length n, and I want communication complexity which is a constant independent of n, though you can have constants depending on other parameters of the problem. Okay, so perhaps the most natural thing that people think about in this setting is equality testing. Alice and Bob have two n-bit strings, and they want to know if they are equal. And it's sort of folklore result by now that communication complexity of this function is order of 1. Just to make sure that we sort of think about things in the same way, I'll also tell you my favorite protocol for equality testing. Each one of us can have our own. A very natural protocol would be Alice and Bob have x and y, and Alice picks the randomness gives them a random index I, and Alice sends x of I over to Bob. And Bob just checks to see if y sub I equals x of I. Now we can see that this doesn't work if x and y happen to be extremely close to each other. And if they differ in only 1 bit, you might only discover this with probability 1 over n. So what do? We just put everything in an error correcting code. So fix an error correcting code, E, which maps Alice's input of length little n to some string of length capital N, where capital N is maybe linearly larger than little n. And we'll now just share some randomness, which is a random index, not of a message, but rather of its encoding. And now the same protocol works wonderfully. You send Alice sends a random index of the value of the code word when you encode x at this random coordinate I. Bob checks to say that these two are equal, and this is obviously a great protocol. And from what we know about error correcting codes, clearly this works with constant communication. Okay. So that's the simplest of examples. And you can pause now and say, okay, now tell me another problem which requires constant communication. Actually, I wrote this paper with Clement many years ago and others. And we tried to show how all protocols of constant communication can now have constant communication in some variant model. And it was only after the paper got into the journal version that we started asking this question. So what is a problem that we can name which actually can be solved with constant communication, which is not equality testing? Okay. So here are some problems. A nice generalization of equality testing is Hamming distance. Alice has x, Bob has y, and they want to know if the distance between the strings is, let's say, at most 1, at most k. Okay? But think of k as a constant, 2, 3, 4, whatever you like. And turns out this actually has communication complexity, which is k log k. So it's a constant if k is a constant. And so in these examples of 2, 3, and 4, it's all constants. And the protocol is not immediate from equality testing. We'll see what it looks like roughly, and then in a minute. So here's an example of another function, which is actually constant communication. Yet another function is disjointness, but for small sets. Okay, so Alice and Bob have sets of size k out of a universe of size n, and they want to know if the two sets are disjoint or not. Once again, if you think about the inputs, even if you encoded the inputs in some nice form, these are inputs of length k log n, at least, or something along those lines. But it turns out that there's a protocol with communication, actually order of k for this setting. So the fact that you can get rid of the n in the communication in both these settings is interesting. And since it's interesting, let me at least tell you very briefly how you achieve this. The rough idea is simple. We want to get rid of the n. What we will do is hash our universe of size n, which is all the coordinates of interest, to some universe of size k squared. If you pick a random hash function, if there are only k relevant coordinates in the input domain, they will get mapped to k distinct coordinates in the hash domain. And once you do this, you have immediately, if you can sort of somehow cast your problem as a problem on k squared bits, you have a protocol which is communication complexity is independent of n. Okay. And this is roughly what happens in both the settings. If you do some more careful thinking and analysis, etc., maybe you get a couple of heavyweight people involved. You get more interesting protocols, but getting rid of n in these examples is not hard at all. Okay. So this is pretty much all the problems that seem to be total functions that I can describe. At least nice total functions. I'm sure there exist problems which depend on only the first k bits, and then those have, but these are problems which are somehow symmetric. Every bit is quite as interesting as every other bit, and yet communication complexities are constant. Finally, maybe I'll just mention one more problem because it's sort of a very nice problem, something that we tend not to think about extensively in communication complexity, but everybody else who's been working with or around communication complexity seems to be interested in this problem, which is the gap inner product problem. This is the real inner product. Okay, so given to Alice's input is a real vector in R to the n. Bob's input is another real vector in R to the n. And let's say these are unit length vectors and they are to norm. And what they want to know is if their inner product is at least C or at most S for two parameters C and S, which are, let's think of them as constant. So even, is it at least plus 1/2 or at most minus 1/2? Okay. And it turns out that for the gap inner product problem, there is a constant bit communication protocol when C and S are bounded away from each other. And this is roughly the basis of the seminal result of Alon, Matthias, and Szegedi. Again, I think it's a very interesting problem. This is maybe also one of those things which is actually most relevant to practice in a sense. This is a problem which has constant communication, and hence many interesting results in nearest neighbor search, etc., are enabled by this result. So perhaps let me skip this thing. Wait, did I lose this? Okay, sorry, something's frozen in my thing. All right, good. Let me skip the insight behind this thing, but I just want to go back to this main message, which is there is this nice philosophical contribution of the notion of communication complexity. In all of these problems, and presumably there are many others which are more specific, not as general, communication is the focus. So when Alice and Bob only want to know what is f of x, y, not all of x or all of y, communication can be much, much less than what you might normally think of as bounds associated with communication. The length of X, the length of the entropy in X, or the entropy of X given Y, etc., etc. All of these can be very, very large, and yet the communication complexity can be very small. Okay. So this was, with this as the background, I want to go back to this question of we want to understand what is shared context in communication, how do you model it, and in particular, one thing that we want to focus on a lot is the fact that Alice and Bob, so example from today, you and I are assumed to know English, but what is our definition of English? Well, we have some definitions which are definitely exactly identical. There is some imperfection here. How do we model these kinds of imperfection? Are there mathematical things, methods which tell us that even small amounts of imperfection can be dealt with? We don't have a general theory. We just have some examples of problems which fit this kind of framework, and I'll try to tell you a little bit about some of these examples. So in terms of how to model shared context, I think from this picture that we had here, sorry, I really have to scroll back so much. Yes, I do. This picture, you can pretty much draw any line which seems to be common to Alice and Bob and look at anything inside it and say, well, that should be considered context. Okay. Alice and Bob assume that they know the function. Well, maybe they don't. I mean, did we agree on what was the function that determines why I'm communicating today? Did not we? And similarly, what is randomness? Well, we can always sort of make that part of this context that we want to deal with, and maybe it's not going to be known exactly, maybe it will be shared imperfectly. So here are some examples of what could be done over here. If Alice and Bob get their inputs from some distribution, and these distributions are not known exactly, okay, so maybe they're sort of roughly similar, or the knowledge of the function, the shared randomness, etc. All of these could be made part of the context, and what we will see today and mention very briefly are examples where we talk about a setting where Alice and Bob don't really know the distribution from which the problems arise. The second setting is one where we will talk about shared randomness and say, well, what happens if Alice and Bob do not have identical copies, but they're just sharing some correlations? And finally, an interesting thing where we will talk about where the knowledge of the function is kind of approximate. So all of these are example settings. In each one of these cases, we have some results, but really what's amazing is the amount of stuff that we don't know about each one of these cases. So I'll also try to give you a sense of what we don't know. Many of these problems have not moved much in a few years, but I'm hoping that when you hear about these questions and get curious, maybe you can make some progress. So the first example, I want to talk about compression, classical compression, Shannon style, Huffman style, and try to say, well, there was some shared context over here. Let's get rid of that shared context, or let's allow it to be imperfectly shared. So what is the classical compression problem? Alice and Bob are given a message which is chosen according to some distribution. And of course, Alice and Bob also know the distribution. But that's the nice thing about this, nice, perfectly synchronized theory. Distributions are known to both Alice and Bob. You don't have to even worry about how they are specified, how big they are, etc. And then Alice wants to send an encoding to Bob of this message. Bob wants to be able to decode it and recover the original message. And our measure of performance is usually the expected length of the compression when the message is chosen according to this distribution. Okay. Now, Huffman coding achieves the optimal performance, and but Shannon had already given a compression scheme which got at most one bit more than the optimal, maybe this entropy of p plus 1. So these are the classical results. And in some work with Juba, Kalai, and Khanna, we asked the question, so what happens if Bob doesn't know the distribution? Okay. Now I want to stress, people often think about this and say, oh, isn't this exactly where divergence as a notion comes from? No, divergence comes up as a notion when the message is not chosen according to the right distribution. But Alice and Bob know the right distribution or know a distribution. When Bob and Alice do not know the right distribution, and this is what will happen with all your favorite coding compression schemes, most of the time Bob will be wrong in the decompression. Just, consider a setting where you're doing Huffman coding or something along those lines, and all the probabilities are almost the same, but some are slightly higher for Alice and others are slightly higher for Bob. You get completely different dictionaries in the two schemes. Question is, can you actually do something in the setting? Well, of course, in order to do something, you have to make some assumptions. It's not going to be that Bob has an arbitrary distribution Q, Alice has a distribution P, and they're able to compress. That's not going to work. What should be working is if Alice and Bob agree on some distance. Well, this is the measure of distance between P and Q, and now subject to this distance being bounded in some ways, can you do something? So our particular definition of distance is this one. It roughly says that for every element, the probability of that Alice associates with it and Bob associates with it are off by a factor of at most 2 to the delta. Delta can be any positive real number. Think 100. Okay, so the probabilities that Alice and Bob are off from each other is at most 2 to the 100. That doesn't seem like a very restrictive assumption. On the other hand, it's also probably a bit more restrictive in that we are requiring this for every possible message. Anyhow, if that's the case, can we somehow compress messages so that the expected compression length is roughly the entropy plus some delta? Most importantly, I don't want the universe from which the message is chosen to play a role in this performance parameter. In both cases, what was really nice is you could have imagined that the message is coming from an infinite universe, a countably infinite universe. And as long as the entropy is finite, we would have had finite communication. Can we get the same performance now? I hope the question sounds interesting to you. I will not have enough time to go over any of the solutions, but what I can tell you is what are the kinds of theorems that we have over here. What we were able to show in the first work with Juba et al. Was that if Alice and Bob share randomness, then you can actually achieve performance which looks like that. Okay. So that's, I think it's a very interesting statement. It's a positive statement. It says there are nice compression schemes, but not the ones that we've used. Well, why not the ones that we use? Because all the ones that we've used have been deterministic communication compression schemes. This one is one which involves shared randomness between Alice and Bob. And the shared randomness is used to overcome the uncertainty between P and Q. Okay, so for every PQ, probability over the randomness that you manage to do everything right is very high. We were unhappy with the shared randomness assumption. So in work with Clement et al., we tried to talk about shared correlation. And I'll tell you about this work in more general setting in a couple of slides. But yeah, you can even get this kind of a performance if the players do not share randomness perfectly, but it's only weakly correlated. But what is most interesting as a challenge to me is the fact that the best result we have for deterministic communication protocols, where Alice is required to compress the information in some deterministic way. She can use the distribution into account when compressing. Of course, she uses the message. And Bob can again use his distribution into account when he's decompressing. We want them to be able to compress and decompress back to the same thing. And we are not able to get a result which is independent of the universe size. What we are getting is a better dependence on the universe size than what you would normally expect. Log of the universe size would have been the trivial thing. You just index all the elements of the universe by different strings. That would have worked. Now what we are able to say is, well, it can be made log of that. Okay. But this is the best that we are able to do. We don't know that this is necessary. And in fact, here's a little cute protocol, cute problem, which seems to capture a fair amount of the challenges behind this thing. So here's a problem. If you haven't been paying attention to everything else that I've been saying, you can just page in now. page out at the end of the slide. You can, this should make sense. We're thinking of communication problem, communication complexity problem, if you will. Alice has and Bob have some ranking of, let's say, N movies. I'll call this a movie today. And what they know about each other's rankings is they're very compatible people. So every movie they rank to within the plus or minus 2 of each other. Okay, so every movie is given a number. It's a distinct rank, one between 1 and n, and for every movie, the rank, the difference between their ranks is somewhere between plus or minus 2. And what they want to know is something very simple: is their top ranked movies the same? Okay. Both of them have a top ranked movie. Which are they the same or not? And with shared randomness, it's trivial to design protocols, which, I mean, you know, it's a special case of equality testing. So of course, it's constant communication. Question is, can you do it without randomness? Can you do it deterministically? And sort of the interesting thing that we can say here is, well, there are protocols which are quite non-trivial, and their communication complexity is log star of this n. So little n is the same as capital N on this page. But, or something related to that. You know, if it's exponential and log star n, I wouldn't know the difference. But it's some small number. But we don't know how to make it a constant independent of n, and we don't know how to prove that as a lower bound. I mean, it's quite plausible that this has got a super constant lower bound sitting here, but we don't know how to prove it. But if it's super constant, it's not going to be a very large super constant. All right, so this is the first of the vignettes that I wanted to talk about. This is what happens if the distributions from which the players are assuming their inputs are coming from, or the underlying distribution from which the inputs are supposed to come from, are not synchronized. Alice thought was P, Bob thought was Q, and suddenly we have lots of interesting questions. For the most part, however, I think of this as a positive lesson, saying, yeah, we still can get pretty good compression, even if you sort of throw that log n away. It's log omega factor from the previous slide. It's not too bad. As we go along, we'll see other examples of such problems and solutions. Again, it's a short talk, so I'll only tell you what the theorems say. I won't probably have much time for any proofs or insights there. All right, so second thing, this is something that sort of came up naturally in the previous context. We said, oh, you can compress information, but if you have shared randomness, but how can you assume that something is shared perfectly when you're trying to assume that other things are not? If you don't know the distribution exactly, why should you assume that the randomness is non-exactly? Okay. So we decided that we should explore this. This turned out to be mathematically quite interesting. I won't say it sort of models a lot of exact problems, but it's also a very interesting space of explorations. It turns out that lots of folks have actually looked at this kind of a setting. Alice and Bob, rather than sharing randomness, share some correlation. For this talk, I'll consider a very simple form of correlation. Alice gets a random string R, Bob gets a random string S. These random strings are generated by getting the pairs R sub I and S sub I independently of all other I, but R sub I is correlated with S sub I. Okay, so R1 S1 is independent of R2 S2, is independent of R3 S3, etc. And each one of these is coming from the same distribution. What is this distribution? Each player gets a random bit, but they're noisy copies of each other. They have some correlation between them, and this is some correlation. For simplicity, let's assume this correlation is positive. Okay. Does this hope I'm making sense with this definition? So Alice and Bob do not have perfectly shared randomness. The only form of sharing that they have in terms of randomness is these shared correlations. Now, this is something that a significant amount of work in the information theory and the information theoretic cryptography community has gone into this problem. They often ask the question, if I'm given such a source of correlations, how can I extract pure randomness out of it? And what they show is that you can actually get away with, if you want to generate k bits of randomness, you can get away with less than k bits of communication, but it's usually omega of k. It depends on this rho, but if you fix the rho and let the amount of randomness that they want to generate go to infinity, they still have to communicate, linear amounts of bits between each other. The exact unknowns over here are exactly what is the constant factor supposed to be for a given source. That's not totally understood yet, but otherwise we sort of know what's going on here. Now, in our setting, usually when we say even equality testing, the amount of randomness that players need is a lot. It's growing with n. And saying that you can get a constant factor saving on the amount of communication is not great. It's by sharing correlation. But remarkably, what one can show over here is if you have any protocol which uses k bits of communication with perfect randomness, you can convert it to another one which has 2 to the k bits of communication with such imperfect randomness. I mean, by imperfect, I'm only referring to this model here. I'm not trying to talk about some very, very general models. Okay? But the important thing is you cannot have done this by extracting from this imperfect randomness some perfectly, perfect randomness, and then using that, plugging that into your original communication protocol. At the same time, you have to use your original communication protocol somehow, or else, how do you get this translation? So it is possible. There's a little bit of a hint about how we get to these results, but once again, so, why do we get the positive result? And by the way, we can show that this k to 2 to the k growth is kind of necessary, and that's shown by some, so we have to identify some interesting problems. I won't talk about it today. I'll move along to the next vignette in this talk. Okay. All right. So for the last vignette that I want to talk about, this is, I think it's a very interesting notion. Our model over here was, I don't think of it as the worst model. I mean, in the previous example, I might say, well, this is not a model that I really love. This one, I do like it a lot, but it's still, it can still be improved upon very, very significantly. Here we talk about this notion that Alice and Bob, do they really know the function that they want to exchange, or that they want to compute at the end of the communication, or can we sort of make even that somewhat approximate? So, so like we said, this goes back very much to the essence of the Yao model. If there was one philosophical reason to be studying it, is because communication can be very short if you don't, if you focus on the function that is being computed. But on the other hand, how do you focus when you don't know what it is? Right? So we wanted to try to understand this. So we started exploring it. In fact, we had the paper almost written when we realized, oh, we haven't really defined the model very precisely. And it actually turns out to be challenging. When we define communication complexity, you always say it's the minimum over all protocols pi, blah, 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 blah. But pi, minimum over what, if the protocol knows the function that is being computed, you can formalize this in whatever sense you want to. If the protocol knows the function that is being computed, then Alice and Bob don't need to know it. They just go ahead and execute the protocol. So you cannot really define this problem completely trivially by just saying, let's take the definition of communication complexity and let's apply it. And I think the reason I want to talk about it here is the underlying graph that oops, once again, I've got frozen screen. Okay, there you go. Once again, there is this. There's an underlying model which should be probably common to all uncertain communication problems. We should really think of the uncertain communication problem as being described by some huge graph, really, really massively huge. What Alice knows is the name of a vertex on the left. What Bob knows is the name of a vertex on the right. What they would like to do is engage in some protocol. The protocol, when Alice is doing her bits, obviously use the knowledge of the vertex, left vertex. When Bob does it, he knows that he has knowledge of the right vertex. But their goal is to achieve some functionality which is defined by an edge. And different edges define different functionalities. And what we would like is a protocol which knows the whole graph, but doesn't allow Alice to know the function, her own input, and Bob to know his own input. So you can take this model, you can specialize it in the setting of functional uncertainty. Alice gets a function f. So all possible functions mapping, 2n bits to 1 bit are vertices on the left. All possible functions mapping 2n bits to 1 bit are functions on the right. You draw an edge between the two if you think that this is a legitimate pair of functions for which you want to see them being able to do something reasonable. So a very natural graph over here would be if these two functions are close in having distance, then you draw a thing. And by the way, notion of success for a protocol, you would ideally like to say, well, we will compute f of xy correctly on every input, or g of xy correctly on every input. No, we can be much, much, much sloppier. We can just ask them to compute some function h of xy, which is close if f and g are close. Okay, so if we draw these edges only if the distance between adjacent points is epsilon fraction, and I might say, look, even if we compute a new function which is square root of epsilon far from f and g, we should be happy, or log of 1 over epsilon away from, or 1 over log of 1 over epsilon away from these two. We are happy as long as the error is going to 0 as epsilon goes to 0. Can we design protocols that look like that? That's the kind of a question, and I will quickly tell you, Rocco, how am I doing on time?
I was just going to mention that you've been going for 35 minutes just now.
Okay, sounds good, thanks. So yeah, hopefully I will finish in 5 and we'll have time for the questions. Okay, so couple of, this is not the order in which we discovered the results, but I think this is the order in which people get convinced that these are interesting questions. Here's the simplest negative result. There exist distributions and, exist problems and distributions where on that distribution you can solve this problem very easily with 1 bit of communication from Alice to Bob. This is not order of 1, that's 1. On the other hand, if you try to do this, with imperfect knowledge of the function, and even like the functions are 0.1 close to each other, or 0.0001 close to each other, etc., communication complexity jumps up to square root of n. Notice that any of these problems can be solved with n bits of communication. You don't need to exchange your functions. That would be stupid. Exchange the inputs x and y. That's enough. But if you're saying we can get pretty close to that, and it's necessary. And this happens when you allow the inputs to come from some skewed distribution. Turns out that, so I like this as a model because it really tells us that protocols are not really continuous with respect to the functions being computed. Alice could execute her F protocol and Bob could execute his G protocol, but they're not going to be getting them anywhere close to the right answer. Okay. On the other hand, there are positive results which roughly say that, look, if you're working with a product distribution, so X and Y are independent of each other, then this kind of a negative result doesn't hold anymore. If you had a k-bit communication protocol, this would be order of k-bits in the new version. And and this is true for one-way communication. If you have only two-way communications, well, a k-bit two-way communication protocol can be translated to a 2 to the k-bit one-way communication protocol. And so you still get no dependence on n in these examples. K-bits get mapped to 2 to the k-bits. So that's, I think, a fairly interesting result. There's some further generalizations. Anyhow, so that's roughly the kinds of results that we have. By the way, the gap between what we can do with one-way communication over here and even a two-round protocol is vast. If it's 1 rounds, then k-bits with perfect knowledge of the function translate to order of k-bits with imperfect knowledge of the functions. If it's 2 rounds, k-bits translate to 2 to the k-bits. That's the best that we know. We don't know if this is actually necessary or not. So another very interesting question that seems to be open here. Future directions, what bothers me now? I mean, perhaps not enough time for me to go over the slides, but I want to just say that, look, I want to view communication as a lens into a lot of what's going on around us. It's a great way of exploring spaces into which we are not given access. And trying to understand what allows for small communication protocols and what doesn't seems to be a pretty good way, just the same way as we've used saying when is computation very polynomial time doable or not, giving us insights into processes. I think communication could be a great lens also. One place that I would love to apply it to is modeling the mind. This is something that came up when we were trying to understand what do people really do when they are trying to verify proofs of mathematical theorems. They invoke all kinds of knowledge, but they're not just invoking knowledge and using it by rote. Not saying, I know, I've seen this theorem with the same value. At the very least, they're able to replace k by n and n by k in some examples. So it's not universal. But they do a lot more. They can often combine statements that they know and so on. What is it that explains that? I want to study it in a communication sense. So let's model the brain by what are its inputs and outputs. You give it inputs of the form, update your brain with the following sentence. You know that X is a true statement. And then you later ask questions of the form, is Y true? And can we come up with good models that explain the intricacies of the answers over here? It's kind of very surprising as what kinds of statements we are able to do, but also what kinds of things we are unable to do in the setting. And these things could even shed light into the architecture of the brain. Okay. That's as much as I'd say. I'll skip some more slides. Just to summarize, whoops, there you go. Just to summarize, perturbing this common information assumption is leading to lots of very interesting questions. They're both, I think, philosophically interesting and mathematically so. And I think there are technical challenges, but there's also more importantly, this uncertainty as a model is, I think, a fun one and probably worth exploring further. Okay. All right, let me stop here. Thank you.
Great, thank you, Madhu. Let's thank Madhu. So we have a few minutes for questions from the audience. Would anybody like to ask a question? You can raise your hand or you can type something in the chat. I'm trying to see the list of all the participants. Let's see, do I see any raised hands? Samant, I see, has a question. Regarding the graph of allowed neighboring functions, what could be other natural examples, things, I guess, besides Hamming balls for how you decide to put edges down?
Right, okay, that's a great question. I mean, I think that is itself a research question in some senses. That's probably the one reason why it's it's not the best of models. We would really like to understand what's the uncertainty between people when they're trying to, decide to engage in a conversation. It's not as if we have some very well-defined function which is very, very close to each other. But there's still some notion of proximity. We seem to have, I think it leads to notions such as, there is hierarchy to knowledge, and we tend to view different aspects of knowledge to be valuable or not. And some measure which preserves these things. But one way or the other, it's going to be some, I'm going to look at some measure of distance between functions, and then put a cutoff somewhere saying, look, anybody who's within a certain distance, I want them to be able to talk to each other. Anybody who's not, I wouldn't. And distance measures could be sort of, I mean, it's a good example in exploration and metric spaces and so on to see what are interesting metric spaces that sort of arise under the setting, and do we get, can we get sort of any interesting protocols when we look at these different spaces? It's a great question. I really don't know a good answer.
Thanks. I see Thachapol has a question. He's making a plea, which I would like to echo, to see just maybe a minute or two on the remaining future directives. I think you skipped over a slide or two at the end.
Yeah, no, I didn't skip over the slides. I skipped the slides before the talk. I wanted to make sure that I was only, oversampling the number of fraction of slides by, factor of 3. And so there were just a couple of instances over here. Here is a proof from a paper by, I believe this is Lineal and, I forget, Kalai and Lineal, I forget. So it's a very short paper. This is the entire essence of the paper. And when I look at this thing and I ask the question, who can understand this proof, right? I mean, certainly many of us can. Even for us, it takes different amounts of time to be able to verify it. But then certainly exists mathematically savvy people who will not be able to understand this proof. So there is a large amount of context baked into many of the things that we speak about, even in very, very concrete settings. I mean, how much more concrete can communication get than saying, I'm trying to verify a proof of some statement? So these are things that we are studying. There's examples that we mentioned over here where, you had this crossword kind of a thing where you say, look, I'm looking at this crossword. I've already got the first letter, it's a J, the last letter is a Z, and the clue says it's a Woodstock performer. How many answers do I know that could fit this thing? There's exactly one. I know the name and I cannot guess it. And then after a little while, I get a few more letters, then I'm able to get it. Okay. So why is it that our brain, what is the structure of our brain which is able to say, I can answer questions of the following type at this stage while not being able to answer it at this stage? Okay. So I think there are sort of lots of very interesting questions purely about revolving around the question of how do we actually in society do communication of very concrete, explicit things like knowledge, mathematical knowledge, which is considered to be unambiguous in some senses. But we don't really we don't understand the process by which we communicate it. We understand logic, but this is not an exercise of logic. That's roughly what I have. There are, by the way, in case you're interested, there are other talks that I have given on this topic where there's a few more examples of things. There's also in this thing a few concrete questions that I'm mentioning at the bottom of this thing, but I don't want to dwell on those now. Okay. I'll post the slides on that.
Thanks. Maybe we have time for one more quick question from Yannick. Do you believe there's an easier way to model the function uncertainty? I guess.
No, I think easier is not the right direction. I think if you're thinking of this massive graph that we're putting in there and we're saying, is this something that we can work with? I think that's just, it's a modeling choice that will become part of our system once we start thinking about this question seriously enough. And so we won't really think of it as a complicated model. It's actually the most natural thing. In terms of, do I really need to think about this huge graph? Yes, we do. We cannot try to focus on a single function at a time and try to capture this problem because it's the ability for us to move from function to function to function that makes the problem interesting.
Great, thanks. Let's all thank Madhu virtually in a distributed fashion again.